Good afternoon, and welcome to the Music and Technology Seminar at Carnegie Mellon. Our guest today is Professor Richard Stern, who has more than 200 publications in scientific journals, many related to speech recognition and perception of sound. When I first met Rich Stern last century, last millennium, it wasn't as an ECE professor at Carnegie Mellon. It was as a harpsichordist. And I can safely say that I have followed his dual careers as researcher and musician well into the 21st century. Please welcome Richard Stern to the Music and Technology Seminar.
Thank you. Thank you very much, Ricardo. I'm going to see if I'm coordinated enough to actually get this going. As I said to Ricardo, I think I've known Ricardo longer than anybody in the building. We first met, if I remember correctly, around 1978. He was I can't tell whether you were the R or the S of RST Electronics. They had the recording franchise at the University of Pittsburgh at the time. In any case, it's great to have him here, and it's great to have all of you here. Now, let me try to actually get to what I was planning to talk about. And I'm going to attempt to grab the screen. Zoom call. Share screen. Being sure to share sound. I'll optimize for view and clip. That didn't work, did it?
We can see it.
We can see it. It's
You seeing the whole desktop or just the PowerPoint?
the whole desktop.
All right, let me back up then. Try one more time. Here it is.
Yeah, there we go.
There you go. All right. So anyway, it's a pleasure to be talking here again. So as you might have already known and saw if you read the abstract, my work over the years as a science and engineering professional rather, has been in the areas of auditory perception, especially binaural sound localization, and speech processing, mostly signal processing for robust recognition, close parens. Most of what I've been doing lately is not so relevant for this group. So after rashly volunteering to give a talk back in January, I had to spend some time thinking of what I wanted to talk about. And so I won't be talking about sound localization or speech processing. I've talked about binaural hearing in the past, but a lot of that, at least for music and technology, has been kind of overrun by things like ambisonics and the other computational sound localization approaches. Instead, I'll hopefully not bore you too badly with reminiscences and stories about knowledge representation in music synthesis and in speech recognition. Most of what I'm going to say you probably already know, but sometimes it's useful to think about. And when I thought about doing this originally, I had planned a much more glitzier talk with a lot of animations and sound clips and demos and things like that. But we're in the middle of a semester. Those of you who were in my DSP class this semester know that I still haven't returned the midterm exams that were supposed to be given back a week ago Monday. And I've just been completely swamped. So this is really kind of the bare bone version of this talk, although the message remains the same. I came to college. Many of you know I was at MIT as an undergrad, and in fact, one of my math teachers was Ben Munkris's grandfather. That places me, I guess. I came in the fall of 1966, not knowing much of anything. And in the first semester as a freshman, I got the equivalent of a 2.5 QPA in using CMU calibration. And the second semester, I got a 2.0. So it didn't look good for future doctor of philosophy. And if you had told me in the spring of 1967 that someday I'd be a college professor at a good university, I can't tell you how shocked I would have been. But I had trouble freshman year, partly because I never learned how to study. High school was too easy. College was not. By the time I got to sophomore year, my grades were in a more respectable zone. But I still was kind of slogging through the double E curriculum at MIT in those days, and had no idea what I'd do professionally. I actually thought I would end up selling shoes or something. But as late enough as the end of the first semester junior year, I had a conversation with a professor that I wanted to do a project lab with, Barry Blesser. And he suggested, since I'd already figured out that I was no good at circuits, that I should think about doing perceptual experiment. And he gave me a bunch of stuff to read, mostly preprints from Audio Engineering Society journals. And they were interesting. And for the first time in my life, I realized that I might be able to combine my long-term interest in music. I had been playing piano since I was about 7, and done other things as well. By the time I had that conversation, I had already gone through my rock band phase and recorded an unreleased album for Kama Sutra Records in 1968. And I was a music major for a while at MIT, which was actually a very good, respectable program. The theory courses were excellent. And I certainly recommend the experience, music theory here, if you're not already taking the courses. But in any case, I also realized at some point along the way, Switched on Bach came along. That was then Walter Carlos, now Wendy Carlos, doing Moog synthesizer renditions of the famous Baroque tunes. And the sounds were interesting. I was particularly captivated with the idea of building a synthesizer that would create would emulate realistic musical instrument sounds, trumpets and violins, and instead of gleeps and tones and noise blasts and things like that. But I realized, again, same year, I was taking a course called Multi-Stage Transistor Circuits, and my transistor circuits were really miserable. I could hardly get them to get biased properly. And meanwhile, the guys in the next, the next lab position over were having this anthropomorphic love affair with their devices. And so, this little guy turns on and he talks to his friend over there about the signal going down. And my transistors didn't do anything like that. And I realized that I was more interested in why things sound the way they did, rather than having any realistic hope rather of being able to build something that would enable them to work that way. So the great thing about my interaction with this professor is that he got me interested in actually going to the library and reading the journals. And one of the first journals that I encountered was the Audio Engineering Society journal, which I'm sure many of you are already familiar with. And I started reading first at random, then started looking at tables of contents. I was really fascinated. I was spending hours in a library, which was crazy, and just really excited about being there. And again, one of the things that I looked at very early on was the study by this guy, Melville Clark, who coincidentally was an undergraduate at MIT in the same class as my father, but as far as I can tell, they never knew each other. And his colleagues, David Luce, Abram Schlossberg, and Rome, they investigated perception of musical instrument timbres. Now, the way they did that was, what they would do is they would take tape recordings of musical instruments and take scissors and cut the tapes and, splice them. This is conventional recording technology of the 1960s. They would separate the first 20 to 30 milliseconds and do perceptual experiments on people asking what instrument they thought they heard. And what they found was that the first 20 to 30 milliseconds had much more to do with how you heard something than anything that followed after that. People couldn't, if you heard the first 20 to 30 milliseconds, you could name the instrument. If you heard the next 2 to 3 seconds, you couldn't. And you can imagine this is true. I'm sure you've all listened to speech or music played backward. And the temporal sequence of things is excruciatingly important. I was also interested in that because I thought that that might be a clue to how it is that we could simultaneously perceive multiple musical instrument timbres when you have many instruments playing at once. Anyway, this study of the attack transients was really fascinating to me, and thought, that's what I wanted to do. There were other people doing, working on, similar problems. For example, Jean-Claude Risset in France was doing physical measurements of the envelopes of the individual harmonics of musical instrument sounds. That diagram on the left-hand side, which I think came from an issue of Physics Today, circa 1969, shows the instantaneous amplitudes and how they evolve over time. And although there's a lot of information in those measurements, and it's hard to characterize things in a very general way, you can learn a lot about, you can learn a little about, if you want to emulate certain kinds of sounds, this is what you have to do to the amplitude envelope. And most of the synthesizers of that day, and I'm pretty sure even of today, have controls like that. So the results are hard to characterize. There's a lot of information, but measurements like that have been used to inform subsequent work. And I actually, when I first returned as a grad student, I went to, when I first returned to MIT as a grad student, I did similar measurements and attempted to do similar syntheses. So I managed to finish undergraduate school, all excited about signals and systems. The signals and systems course, which I think was actually called Signals and Systems there, we didn't get in the normal curriculum until second semester, junior year. So I didn't have much time after that. I was already wondering about what to go next. But thinking about the interplay between the time domain and the frequency domain was, tempted to say transformative. And I mean, no pun intended whatsoever, but it was really very exciting to think about these terms. And I thought that I would study communication theory, information theory in graduate school. I applied to 5 grad schools, and I got into every one except for MIT. I was on the wait list for MIT. And during my spring break senior year, I took a road trip to California. I'd never been west of eastern Pennsylvania before then. And I flew to California. That's where, this is the 1960s, is where you get your shit together and everything is groovy and all right, man. So, it had this sort of intrinsic fascination. And I visited Berkeley and I visited Stanford. And I concluded that Stanford was really the place that had the programs that I would most serve my needs. But I went to Berkeley instead because I wanted to live in Berkeley. Palo Alto seemed a lot like the suburbs that I grew up in, and it just wasn't very appealing. I kind of joke about the fact that I studied DSP with Oppenheim, pattern recognition with Duda, and acoustics with Bose. And you may not know Duda so well, but he is equally famous in pattern recognition as Oppenheim and Bose were in DSP and acoustics. And what I say is I had to go out to Berkeley in order to pick up Duda in that triumvirate. But while I was there, I had a high school friend of mine named, you don't need to know his name, but I had a high school friend who was also a first-year grad student at Stanford doing English. He went on to become the director of a computer learning program called the Learning Company. They had students here are probably too young for that. And later he was a vice president at Mattel, but he hated it. Didn't want to work for Ken and Barbie, he told me. But David had this friend who was in music and took me up to where Karma was in those days. And I talked to John Gray, who was doing thesis work in musical instrument timbrers, much more interesting work than I've been doing. And I met this guy, John Chowning, in the spring of it would have been the spring of 1971. And we talked for the better part of an afternoon, and he was talking about a bunch of stuff, did some demos of some of his compositions, and was talking about this new thing he was experimenting with called FM, frequency modulation. And he was describing to me this series of phenomena that he had kind of stumbled on serendipitously by taking conventional tones and then frequency modulating them, and then by cranking up the modulation frequency and cranking down the carrier frequency in ways that you wouldn't normally do in FM radio broadcast, you get a lot of interesting spectra, and I'll talk about that in a second. The thing is that simple frequency modulated signals have many spectral sidebands. This is when I first came to Pittsburgh, when I first came to CMU, I taught a course. Tom, I don't know whether you ever took this. It was the communications course. And we would talk about, among other things, how amplitude modulation worked and how frequency modulation worked. And this equation here, S sub Fm of t, is representation of a cosine of frequency omega 0 that's modulated in frequency by a sine. And technically, this is phase modulation, but if you take the derivative of that, you get frequency modulation. But if you just take that equation as it is, that parameter beta is the phase deviation or frequency deviation parameter. And that's actually a very complicated, it has a very complicated mathematical representation. One of the things you can show is that the Fourier transform of that breaks down into something that can be characterized as a large number of cosines at adjacent frequencies whose amplitudes are Bessel functions of the nth order as a function of the modulation frequency. This is, I used to know how to do the derivation because I taught it, but it certainly is something that I wouldn't have stumbled on. And I don't think Chowning stumbled on it either. He just played around with the parameters on his synthesizer and heard some interesting sounds and tried to figure out why it worked the way it did. But anyway, if we look at this, the left-hand panel here is the actual spectrum of an FM synthesis of an FM, basically just the equation that I have there, the sinusoidally frequency modulated or phase modulated signal. The nominal carrier frequency is omega 0. And then you have these side frequencies that are all integer multiples of the modulating frequency, which is omega sub f here. And you can see that you have these side lobes, and each of the sidebands has, think of them as delta functions, but each of them has an area that's equal to, or at least proportional to, the Bessel functions. And some of the Bessel functions are negative, and some of the Bessel functions are positive. Now, that's what the FM signal will look like, if you're actually broadcasting over, say, WQED or WYEP. But what you can then do is multiply this whole thing by another cosine, the whole thing by cosine at the carrier frequency, omega 0. And that'll bring this cluster down to 0 to the left, and the clump on the left will go to the right. And the various components will interact with each other. Some will reinforce, some will cancel. And this whole thing happens in a very nonlinear fashion. What we're looking at on the right-hand panel is a plot of spectral magnitudes. Note that these are magnitudes here, so all of the arrows are positive. As you increase the modulation index, that's beta here, which is the same beta that we have over here. As you increase that modulation index, you get more and more power concentrated in the side lobes. So you get things that are brighter and brighter and brighter. And once again, you can take this signal here and translate it down to baseband, and you'll end up with a very rich sound, a very harmonically rich sound that's controlled by a relatively small number of parameters. As Chowning identifies in his paper, which is an interesting read. This was from the Audio Engineering Society Journal, I think in 1973, 1974. It's easy to find, or I can send you a copy of it. As he points out, what matters for the kinds of sounds you get is the ratio of the carrier frequency omega 0 to the modulation frequency, whether they're an integer relationship. With a right choice, with a good choice of parameters, you can get signals that have signals that have only the odd harmonic components, which is what woodwinds do, and other and flutes to some degree as well. With by varying the beta dynamically in time, you can simulate something like these very sharp attacks that you hear in the brass instruments. But the important thing is that with a very simple structure, with a small number of parameters, you can create a fairly wide variety of interesting sounds. Now, caveat here, one of the things I had initially intended to do was give you a MATLAB demo with some of these things with different values of the parameters, including some of the ones that Chowning had in the paper. Didn't get to do it, sorry. But it's all out there. You can try it yourself. But of course, FM synthesis has, to some degree, had its time. Do I see something in the chat? I think I do. 1 second. Yes, absolutely true. Interestingly enough, oh, thanks, Tom. That's very sweet. Interestingly enough, the frequency modulated square wave and the frequency modulated sine wave, these are the only two signals that you could do analytically. But typically what we try to do is we try to, instill in the students what actually tends to happen. And that's pretty much all that you need to know. You need to know the bandwidth, why FM works, and in particular, why FM is noise resistant. This is all interesting material, and it's really largely courses that are no longer taught anymore. Because with the advent of digital communication, which is pretty much everything now, those techniques aren't as interesting as they used to be. But again, the fact that things change the way they do is you increase the modulation index. That's a consequence of the relationship between the modulation index here and the argument of the Bessel functions, which maps to the amplitudes of the side lobes. So, by the way, interrupt me at any time for questions or comments or your own reminiscences. But let's see. So, moving on. So, when I was a freshman at MIT, I rushed for fraternities. That's what everybody did. I didn't end up in one. But one of the guys in one of the fraternities, who was a sophomore when I was a freshman, was this person I was introduced to as Kurzweil. And if I'd known what would happen to Kurzweil, I probably would have paid more attention to him at the time, but I didn't. So Kurzweil, of course, went on to do a lot of interesting things. The first thing he did was he built a company that did a reading machine for the blind. It was a commercial reading machine. Everybody talked about what a great inventor he was, and how clever and original this was. My initial reaction to that was not being very impressed, but because I knew that what he actually did was there was an ongoing research project at the MIT Research Lab of Electronics, which I was a member of, different group. But to do a reading machine for the blind, you need to have two things. One is you have to have a video thing that scans and then interprets the scans, something like what we now call an OCR machine. And then you have to have something that interprets the scans, turns them into words, and then turns the words into sounds using text-to-speech synthesis. Both of these were known technologies, and I was kind of somewhere between condescending and dismissive of Kurzweil's efforts at the time. But the truth is, I've come to appreciate a lot more in the years since then how difficult it actually is to convert a laboratory project into a commercial success. So when the next Kurzweil comes along, don't knock him just because you've already seen the work somewhere else, especially in the university. It's a lot of good work, and he's done a lot of good things. Anyway, the first thing he did was this reading machine for the blind. He sold the reading machine company, I'm sure for a lot of money. And then with that, he founded 3 new companies. One was another OCR company. Second was a speech recognition company that I had a lot of interaction with over the years. And the third, of course, was the music synthesizer company. Ray Kurzweil had also been interested in music as well as science and engineering for at least as long as I'd been. He was able to turn it into much more tangibles than I had been able to. The insight, so because of his work in doing the reading machine for the blind, he became friends with Stevie Wonder, who, as I know you all know, is a blind musician, and was, in the peak of his superpowers around the time when all this was going on. And Stevie Wonder said to Ray Kurzweil, can't you build a better piano, electronic keyboard? And in my old rock band, I had a Wurlitzer 140B, which was this mechanical thing where they would have these magnetic bars that would get hit by hammers, and the bars would go out of tune, and you'd have to increase the frequency, you'd have to file the part of it down. To lower the frequency, it was tougher. You'd have to add solder to a piece of it. And it was always trial and error. So it was a very imperfect product. Kurzweil had the insight, which was substantial, of recording real pianos. So if you want to synthesize a piano, record a lot of pianos, record every note on some representative piano, and record it with the notes playing softly and then mid-range and loudly, because of course the harmonic structure, the overtone structure changes. And when you're done with that, you got that. So what was interesting to me was that the knowledge representation problem had gone from the 1960s, in which we were really trying to figure out how real instruments worked and what the physics of modern instruments might have been, to in the 1970s with FM synthesis. We were in what John Chowning was able to do very effectively. Of course, he got a lot of good attention for all the right reasons for this work. But now we don't really care anymore about how the real instruments work. What we want to do is find out a way to represent things just model it using a few parameters that we can control, until finally in the 1980s, when Kurzweil was doing his original work, really what he was doing was sampling real sounds, and the engineering technology was just simply being able to synthesize the sounds or stitch the sounds together in a way that didn't give you very many artifacts. And there are papers on this, what to do about the face. And I think Roger worked on this problem at some point, if I'm not mistaken. Roger, feel free to chime in. But the nature of the problem had changed, and to me, it wasn't as interesting. There are a gazillion clips of the first product. This is a Kurzweil K250, the original 1984 commercial product. only play a few seconds.
Rich, I think it's coming through your microphone. Can't really hear.
Is the audio coming through there?
That's
That's
kind of,
better, right? Wasn't that better?
yeah,
Say that again. Could you hear anything?
yeah.
Oh, okay, good. I only played a few seconds because, you know, frankly, it sounds like any other digital piano you've heard now. It's, I, I think the upper notes sound pretty good. The lower notes, not so much so. But nevertheless, it was a big advance. And of course, the piano was very popular. And now this is now the dominant technology. I've played many things like that.
Rich,
So-
can I jump in with a couple of Kurzweil
Yes, please.
comments?
Please.
Yeah, it's just interesting. It always kind of bugged me that Kurzweil called this a digital piano because it's actually a hybrid. The problem was to do pitch to resample the digital recordings and do it cleanly, as you know, is kind of a substantial computation, which they didn't have the digital horsepower to do that. I mean, we do that, like every digital audio workstation does that in software now on scores of voices, but at that time it wasn't practical to do it with digital hardware. So it actually had I think it had 10 separate digital to analog converters, and each one ran at a variable sample rate. So they would, actually pull the samples out at a variable speed, run them through the D to A converters, and then after that it was like analog mixing and filtering to produce the output. So that was kind of interesting. And the other thing is I talked to a bunch of guys that worked on the sample libraries for the Kurzweil, and surprisingly, recording pianos was they found incredibly difficult. I suppose because of the soundboard and kind of the three-dimensional aspect of piano sound, that when you get it down to just one sample, getting something that sounds good and uniform across 88 keys was very difficult. And so some of the piano sounds were actually, highly manipulated and processed. And there were some other voices that they used a lot of synthesizers rather than recordings, just because it didn't matter. The only thing that mattered was the ultimate sound quality of the samples.
Yeah. Well, it certainly did sound good in the end.
Yeah.
And I know it had a big impact. All of my, and even though the original ones were quite expensive, but all of my serious keyboard friends who were in the business, so to speak, were very positive about it. Anyway,
Yeah.
So let's talk about what we've seen. I sort of alluded to that before, but early work was measuring the physical parameters and how musical sounds were perceived. Then we went into this phase of pragmatic parametric modeling of musical sounds. That's my generic characterization of FM. And then direct recording, storage, and concatenation of musical sounds. And I should mention, by the way, that my colleague, now retired Alan Black, in the LTI, Language Technologies Institute, had a speech synthesis system called the Festival system, or FestFox system, that was very realistic TTS. And this kind of recording and concatenation of units was exactly the way things were done until very recently in text-to-speech synthesis as well. And finally, although I haven't talked about it explicitly, and will not until go through the second story, which I'll have to rush a little bit, we'll talk about blind learning without any domain constraints using techniques based on deep learning. Okay, so let's back up and jump again. It's now 1977, and I'm finally out of graduate school, and I go to this place, Carnegie Mellon. While I was at MIT, I had basically zero interaction with the computer science people. They were off somewhere else in Tech Square, where all the AI stuff was going on. But artificial intelligence was a big thing here. I was the ways of and in general, it was claimed that what AI was all about was having machines mimic perceptual processes or cognitive and perceptual processes. And some people would go in to even suggest that by being able to do that, you get insight into how human thought worked, which I thought was crazy. Just beginning with the differences in a single complex processor versus tens of thousands, if not hundreds of thousands of neurons. Remember, this is before neural nets. But in any case, the two basic things that people were looking into were mostly knowledge-based approaches. The real action when I arrived in January 77 was in expert systems. So, for example, if you wanted to build a machine, and there's a very famous one over at Pitt at the time, I might mention, that would do medical diagnoses. You'd interview a gazillion doctors and find out, how do you diagnose the diseases that you diagnose? And they would give you this laundry list of symptoms. If you have a this, it's that, but not if this other thing is above this threshold. And it was this huge, enormous compilation of ad hoc observations that they teach you in med school. I suspect they still teach you that stuff in med school. The computer scientists would attempt to come up with ways of representing these production rules in lists of things, and there'd be ways of resolving conflicts that inevitably would happen when the application of one rule contradicts what the application of some other rule with the same input would give you. But that was what was going on. This is the kind of thing that Herb Simon and Alan Newell were doing. I remember a lot of theses of the day on expert versus novice, knowledge representation. What do expert people know that beginners don't know? This was what the high priests of artificial intelligence were doing. Meanwhile, over in the corner, there were a small number of malcontents who were doing things based on statistics. They were typically, I would say the attitude was somewhere between condescension and derision. And I would hear this stuff because I would go to the computer science cocktail parties and things. The lounge used to be on the fourth floor of Wheaton Hall. Roger, I'm sure will remember that. The statistics people didn't have much street cred. Now, in the early 1970s, there was a big DARPA program in speech recognition. The task was pretty ill-defined, but it was to recognize "quote unquote" large vocabulary with minimum training, stuff like that. And there were four or five major sites that developed systems. One of them was MIT Lincoln Lab, one was BBN. There was one from Sperry, I think, and I forget what the other one was. But Carnegie Mellon had two systems. One was called Hearsay, and the other was called Harpy. Again, this is in the early 70s. CMU won the competition by a country mile, although the other sites grumbled that we kind of cheated because the systems had a lot of constraint from a lot of other things. But that wasn't against the rules. It was just being smart. It was Raj already working the problem. But the Hearsay system, here's a block diagram about it. And I won't say too much other than to say that it was complicated. There would be, something that would recognize phonemes, something else that would recognize words from the phonemes, and then sentences from the words. And all of this would be done in the context of knowledge about the world and the language and the nature of the task. I'm not going to run you all the way through there, but let me give you a very brief clip from the days, and that illustrates the working of the systems. Here it is.
Learn a language with great TV.
Stellen Sie sich vor, Sie würden in die Vergangenheit reisen und dort
I think you need to share the.
This is Bach, by the way. This is the musical content of this talk.
At Carnegie Mellon University, we have been working towards a system for speaking to computers.
And I have to say for a moment that for the old timers here, this is startling because this is Raj Reddy, the founder of the Robotics Institute, former dean of the Computer Science College, as a much younger person.
Hey, we're hearing this, but not seeing
We
it.
will try to show the problems that
You're not seeing it?
No.
Oh.
I think you've only shared the presentation, so.
Oh, all right. Let me, I'm going to pull out of the screen sharing and go back in again so you see the whole screen. Sorry, I'm glad you told me. All right. Give me a second. This time you're going to get the desktop. Okay, here it is.
that arise in getting a computer to understand
Can you see it now?
speech.
Yes.
We all know that a native speaker uses, unconsciously, his knowledge of the language, the environment, and the context in understanding a sentence. This knowledge includes the characteristics of the sounds, the stress and intonation patterns of speech, a dictionary of legal words, the grammatical structure of the language, the meaning of words and sentences, and the context of the conversation. To illustrate the problems of speech recognition by computers, let us examine the sentences we heard earlier and their inconsistencies with some of these sources of knowledge.
Colorless paper packages crackle loudly.
Colorless yellow ideas sleep furiously.
By the way, that's the voice of Alan Newell, the Newell of Newell Simon Hall.
Sleep rises dangerously young colors.
Ben burada ne yaptığımı bilmiyorum.
Now we'll try a different experiment. I'll say a sentence and you try and write down what you hear. In Mariozar, in Kleinanar, in Pine Tar is in...
Okay, I'm going to abort the video because time is short, and I want to say a few other things as well. It's easy to find on YouTube. Just look up Hearsay System, and in fact, there are much longer ones. This was a classic example of the knowledge-based, what you would get with a knowledge-based approach. Now, the Harpy system, on the other hand, was the complete opposite. You would start with embedding, you had a task, you would embed every single legal sentence inside that task as a network. So here, this one is please help, this one is please show everything or something, or please show me everything, something. I think those are subnets in there. Then inside each of the networks, inside of the grammar, you would have the words as well. We already see the sentences and the words inside the sentences. And then inside the sentences, you'd have the phonemes. This looks like please. And you know that the please could be pronounced either with a Z or the S at the end, and it would be about the same. So that'd be a network representation. And the task of the Harpy system was simply finding the best path from the beginning to the end. And again, a lot of work was done on search, but the task was basically not unlike dynamic time warping, which is part of Roger Dannenberg's score following and many other kind of related things. So the hearsay system was way more interesting to computer scientists, to psychologists, to linguists, to pretty much everybody in the world. Everybody found the Harpy system boring, but the Harpy system was a little bit better in terms of having a lower error rate. So it was the Harpy system that won the competition. And this was the kind of precursor to bigger things that happened between statistical and knowledge-based approaches. The ANGEL system, ANGEL is an acronym for a New Generation English Language System. This was a product of ours, a knowledge-based system from, as you can see, from the early 1980s. The ANGEL system was probably the most spectacular failure that I've ever been associated with. I was told years later that we were just 3 months away from being cut off from the DARPA program funding, which would have been a disaster, except Kai-Fu Lee came along and introduced the first Sphinx system. But basically, this is a rehash of hearsay with better implementation. There'd be a word phoneme extractor, then a word hypothesizer, and then a sentence hypothesizer. I was the head of the sentence group. Alex Rodnicki was the speech, or it was the word group, and Ron Cole was the phoneme group. It just didn't work. And there were a lot of reasons why it didn't work. And I'm not going to go through that, but I think the most important one, and it's the one that's the most inevitable, is the fact that it just was not possible for humans to identify and model all the important information by hand. Ron Cole would be down on the floor with literally hundreds of speech spectrograms staring at them, trying to understand the difference between a D and a T or an M and an N, and then code that into something that would work specifically. And it was just too complicated. You can't do that. But of course, that's the kind of thing that statistically based approaches can do really well. The ANGEL system was superseded by the hidden Markov model in its doubly stochastic process. This was the dominant technology for speech recognition throughout the 80s, the 90s, and the aughts until sometime 5 to 15 years ago, depending on how you count, it got supplanted by deep neural networks, deep learning approaches. But basically, you have a doubly stochastic model. One of them characterizes the probability of going from one state to the next, which are assumed to represent, at least indirectly, the underlying phonemes that are used to pronounce things. So this is a representation of the word sit. And you can imagine starting at the start node and then hanging around in the S for a while. And the second stochastic process is, given that you're in the S, those red curves down the bottom, those are spectrums of what the thing you're going to measure. So you look at the audio coming in, you estimate the spectrums and the frequency responses in 25 millisecond chunks, and then use that to compare to the characteristics of a stored model. And that worked really well for a while. Now, of course, everything is deep learning, and this is a trivial diagram of multi-layer perceptron. Much general, more rich characterization through the use of multiple hidden layers. The network organization is typically driven by input-output relationships without any regard to what's going on inside, except at a very clear level. And also, there's very small amount of transparency concerning what's going on inside. It's very hard to figure out what's in the black box, especially since in realistic systems the number of nodes is phenomenal and very difficult to characterize. So what do we have here? What we've seen in both, we've seen in the speech side, but what we saw in the music synthesis side was kind of a steady progression from knowledge-based approaches to statistically based approaches in problem solving. We see this also in artificial intelligence. As I said, in 1977, the superstars of AI were the knowledge-based guys, and the statistics people were just kind of boring number crunchers, didn't have any street cred at all on the 4th floor or the 3rd floor. By the time we get to now, everything is completely flipped. What blows my mind is when people refer to AI, what they're referring to is deep neural nets and the way you solve problems that way. I said to Raj Reddy, I said, this is crazy. It looks like the field has done a complete 180, that we've gone from knowledge-based characterization being AI to very large, very effective statistical models being AI. Is there some contradiction here? Raj said no. He, ever the diplomat, always sees things as looking at the whole and just an evolution of the best technology. The question is this change from building systems based on your understanding of the universe to this black box that doesn't tell you much, is that a good thing? Well, if you're trying to build a speech recognition system, you don't want it to work really well. Yeah. And again, I believe that the dominant reason why this stuff is so successful is that automated knowledge acquisition is much more comprehensive and effective than human knowledge acquisition. Of course, the reason why the DNN approach is much more feasible now than it was, say, in the 1980s when neural networks were first introduced is a combination of hugely better computation, a bit better understanding of the basic algorithms, but that's small compared to computation. And then the third thing, which is even more important, is the availability, at least if you're Google, Microsoft, Apple, Facebook, or maybe the National Security Agency, of a huge amount of data, an inexhaustible amount of data. So you can learn a lot just by paying a lot of attention to the data. The more interesting question for me is this good or bad for creative applications? Maybe it's good. We can certainly build better musical instruments than we could before. But what I don't know, and I'd love to hear somebody else talk about this in some future Tuesday, whether the modern approach is any better at creating beautiful or interesting art or music, whether it's any better or more effective than older techniques. We've had computer music, and of course, many of you, I don't mean to offend anybody among the people in the room who work in computer compositions, but question for me is, have I disappeared from Zoom? Oh, I have to give up the screen. Sorry. There we go. I assume you can still see me. I guess you can. I can still see me. So the question is, are we any better off or worse off? I don't know. But for me, it's interesting to watch, and we'll see what comes. Things have certainly changed from when I was a student. Anyway, that's all I have to say for now, and which is good because I'm already 5 minutes over. But if anybody has anything to add to that, I'm all ears. And thank you, Ricardo, for inviting me.
Thank you for volunteering.
Hey, thanks, Rich. I have one I don't know, comment or question or point or something. You began with pointing out this paper from who was that? Melville on
Mel Clark. Yeah, his an audio engineering society.
On
The
onset.
funny thing, my recollection was that it was in JASA, and I spent a long time looking for it and couldn't find it. And finally, I thought maybe I misremembered. Yeah.
So anyway, one of the people I had the great fortune to study with was Arthur Benaid at Case. And I remember one of his lectures, he was talking about this, and I think we didn't talk about, or I never saw that paper, but I think he must have been referring to this paper because he was sort of on a tirade about these claims that the onset is the key to identifying.
Believe it?
And I think he would agree that there's a lot of information there, but what he was really complaining about, because he spent a lot of his career learning how to accurately measure spectra for instruments. And what he said is that if you sort of properly capture the spectrum, which a microphone in a room does not do a very good job of. He said that instrument timbres were, very clear. It was very easy to identify instruments, and he had actually done experiments with that. And he said if you record and reproduce the spectrum properly and carefully, it has, you get a very different result.
Right. So again, it's an interesting thing to hear. I knew Arthur Bernade, of course. In 1986, he was the general chair of the Acoustical Society meeting in Cleveland, they've had a couple, but that one, I was the rep for the psychological and physiological acoustics group. I read the papers and I had some conversations with them around that meeting. It was driving to the meeting when the Challenger blew up, which was my dominant recollection of that was where I was at the time. But I really, with all due respect, my gut feeling is that you can't capture everything just through Fourier transforms. And again, the example of listening to speech or music played backwards to me is very telling. It doesn't sound anything like it sounds played forward. But of course, we can time reverse short time Fourier transforms. If I get some time in my, if I ever retire, one of the things I'd be curious to do is to try to replicate that experiment, which it's got to be much easier to do now than it was then. And there. One thing I didn't say is that I actually met Clark. I was working, Campbell Searle, who was my undergraduate advisor. I was talking to him about these experiments. He was equally fascinated. He said, he's probably around. He had retired from MIT, but sure enough, he was living out in the western suburbs. And so we drove out to his house in the middle of the winter, some winter, my senior year in college. And I remember it was snowing and miserable weather. And Luce also came in. And he was kind of a bitter guy. His career was like in nuclear physics and like, who was it in our physics department who did this? I'm blanking on his name, but somebody here will know. Late in life, he started doing the musical instrument experiments. And he was very upset that MIT wouldn't fund them.
Schumacher, I think, is.
Yeah, it's Robert Schumacher. Very, very nice guy.
Yeah.
Yeah, very, very good guy. And this was similar background, similar interests. We'll try it. We'll see what happens.
Yeah.
Are you doing any of that work now?
I'm sorry, say that again?
Are you doing any of that work now?
No.
Yeah.
I just, the main, I think, point he was trying to make is he'd been doing a lot of work on what happens in a room and how does music actually, get from the instrument to the ear. And one of the things, an important point is if you have an unmoving instrument and an unmoving microphone, you get like plus and minus 30 dB differences at different frequencies just because of resonances in the room.
Yeah, you'll get that just from the normal modes in the room, especially regular modes. Yeah.
Right.
Yeah.
So if you're not careful with recording and what you're listening to and everything.
Oh yeah, no, we had. I'll tell you a story sometime. We had a horrible time with that in another context.
Yeah.
But yeah, that's a real thing.
And that's a situation where an onset is going to carry, much more information. Like onset information kind of cuts through the room resonances and modes. So.
Well, you get that before, before the reverberant components come.
Yeah.
That's why presence effect works.
All right, you have a chat question.
I see that. How do you think the new deep learning methods will impact applications in low resource languages and music? I'm not sure what the low resource music might be, but certainly. So you're probably aware there's a lot of interest in low resource languages, getting language technologies to work for them. There are groups at the LTI, both historically and now. And many of these are, indigenous languages. The concern is the languages are disappearing, and with them the culture associated with them. The best thing that I could say is, it's going to sound a little prosaic, but the deep learning methods, when applied, everything's going to work better. So both the analysis and the language tools will be better. The real challenge, though, is the human part, to find the dwindling number of speakers of these low resource languages, to capture the language, to learn the language, and then to be able to teach those languages to people who are willing to listen to them. Because what usually happens is people in these isolated communities, once they get exposed to big city culture, they want to be, they want to be New Yorkers, or at least Pittsburghers, and not stay out in, on the farm and rural, wherever they are. That's interesting. Yeah.
Yeah, apparently more than half of the text on the web is machine generated now.
Oh, that's terrible.
Oops.
And for a long time, some ungodly large fraction was in English.
So my background, of course, is not in the scientific analysis of sound and speech. But from what reading I did many, many years ago, it was clear to me that everyone thought that that very initial sound was the most important part of recognizing a musical instrument. And that because Kurzweil and all the people who made keyboards that had different sounds in them had to patch together the initial attack of an instrument sound followed by its resonant sound that went on for much longer than the initial attack. Is that still the prevailing knowledge?
Roger, you're probably better at answering that than I am, but it doesn't surprise me.
I would say that's the case. I mean, in our work, we got I thought some very convincing brass, trumpet sounds and other instruments, saxophone, and they were very convincing, except when you listen to them, you knew something was wrong at the beginning. And we ultimately sort of used a hybrid approach where we could have very good continuous control over the evolving spectrum over the long term, but we combine that with sampled, a small library of sampled attacks, and that kind of solved the problem, because that gave us, the initial transient, which was important, but actually the specifics of it don't seem to be that important. Like from, no matter how the note's going to evolve, you can start it with the same sample and it'll be convincing. But then you also need control over the evolution of the spectrum on the, on the longer term.
Yeah, I think even, in John Chowning's work, he talked about paying a special, kind of manually fiddling with the onsets, but he would do that by manipulating the parameters in the FM synthesis, making them time varying. I think, people would use, they would use measurements like Risset's measurements, though not necessarily Risset's measurements. Of course, it's easy enough for the rest of us to do. And a lot of the things that people like, the Karma group would talk about were ways of developing tools to do that sort of characterization. Andy Moore and who's the guy who just retired? I'm blanking on his name. Maybe just retired. It might have been 5 years ago.
So I want to add one little thing, and I don't know what to make of it. I work as pianist and just observer of music teachers and music students for many, many years. And I noticed that the teachers here in the USA always had emphasized the consonant. Of course, singers can't really sing a consonant. They have to sing a vowel, but the vowels are always separated by consonants. And in order to make what they were singing clear, their teachers always told them, make sure you enunciate, exaggerate the consonants. And this was true for whatever language they were singing in. I go to Italy and the teachers there were saying just the opposite. Get rid of the consonant. Go right to the vowel. Minimize the consonant, but just make sure it's the right one. And I'm thinking, how can that be right? Because everybody in the United States was saying something different. Then I went to the opera in the arena in Verona, and I could understand every word that the Italians were singing with their very short consonants. And I realized that the consonant in speech, as long as it's accurate between B and D and T, and very forward in the mouth, the word would make sense and could be understood easily. So I don't know what to make of that. It was just a difference of opinion and a difference of style. But to this day, I always listen for the consonants and hope that they are very, very short.
The consonants are hard to represent. That's what you lose when you have limited bandwidth. That's what you lose when you have highly reverberant room acoustics. And it's interesting to me to hear you characterize the Italians as being more vowel focused. It could very well be. It sounds like a difference in style.
I would say. Okay, are there any other questions?
Thank you all very much for listening. Yeah, we'll see you next week.
I can stop recording and thank you very much, Rich. I
Thank
really
you so
appreciate
much.
it.